Good morning. Today we begin a new chapter, and this chapter is on solidification of binary alloys. Now, the topics which are to be which we will be covering are listed here. We will first start with isomorphous system. We will define what it is, what is the cooling curve. We will also derive an expression which helps us to find out phase percentage, which is known as lever rule. Then we will make a distinction, look at what kind of material, say suppose an ideal, what is the ideal and what is a real solid solution. We will also know about, we have introduced a concept of free energy, which defines the stability of phase. We will see that how the stability of phase changes with composition. Then we will look at the solubility limit and 3 phase equilibrium, and under this some of the common 3 phase equilibrium we will take up is eutectic, peritectic, monotectic system. We will talk also about transformation that can occur in solid state, and under this we will consider few cases like eutectoid, peritectoid, monotectoid system. Then we will try and look at how to interpret or how to construct complex binary phase diagram involving many of these transformation processes which are listed here. And until this we will consider that the solidification process proceeds in a very slow manner, so that at every point there is equilibrium is maintained, thermodynamic equilibrium is maintained. Then we will look at if there is a departure from equilibrium, what kind of effect do we get in the process of solidification and the structure that evolves. We will talk about dendritic and columnar structure, and we propose to cover this in around 7 to 8 lectures. Now, first let us look at binary isomorphous system. Let us consider two metals A and B that are soluble in all proportion in both liquid and solid state. Now, we have looked at it earlier while dealing with crystal structure. When can this happen? In liquid state, the miscibility is well known. Most metals, they are soluble in each other in all proportion, and but in solid state only those metals, they are soluble in all proportion where certain conditions are satisfied, like both metals have same crystal structure, same valency, almost similar atomic size. So, these are the criteria which determines the extent of solubility of one metal in another. Now, let us consider an ideal case of two metals which are soluble in both liquid and solid state in all proportion. And we learnt about thermal analysis, and this is a powerful tool in determining the transformation processes in alloys. And let us look at the typical cooling curve of pure metal A. If here it is liquid, and as you start cooling, the solidification begins at this temperature, and after certain time when solidification is complete, again it starts cooling down. But when the solidification proceeds, the temperature nearly remains unchanged, and this is the melting point of A. So, let us say we write it as d A. Similarly, metal B, if you cool, it also will have identical or similar cooling curve, and here the melting point, this step in the cooling curve indicates melting point, that is T B. Now, what happens if we mix up the two metal A and B in the liquid state? Now, in a liquid state it is much easier to mix metal, because apart from diffusion, we talked about diffusion primarily in solid state, and we found that diffusion is a very slow process of mixing in solid state. So, all alloys are made by melting and mixing, and when you mix, apart from diffusion, you can stir the metal, and then the diffusion, since the diffusion also depends on the state of the material, state of the matter. In liquid, the diffusivity is much higher. So, therefore, mixing is much faster, and once they are mixed in all proportion, and then you start cooling the metal, that alloy made up of A and B. And say if you look at that cooling curve, it may have behave something like this. It does not have a step as over here, and this solidification possibly will begin this alloy at a temperature which is little lower than, depending on the composition, lower than the melting point of A, and it will be completed, that process of solidification will be completed at a temperature will be little higher than the melting point of B. And so, this we can say that T L, we say that define that this is a temperature at which solidification begins, when crystals of an alloy alpha we say that this is a solid solution of B in A, or vice versa, whatever you may say. So, this is the solid solution which is forming, and so there will be a temperature range when both the phases can coexist, liquid and solid can coexist over a temperature range. And after the solidification is complete, it starts cooling almost maybe nearly same rate as this. So, by performing this experiment on an alloy, we can get two temperatures, T L and T S, and these are functions of composition. Both of these are function of composition. That means, we determine this particular case T L and T S, we determine for a particular composition, let us say 50% A, 50% B, 50% B. So, for this, so that means T L, this is a function of composition. So, also T S is also a function of composition, and here we conduct most entire experiment, because we are conducted at constant pressure, and we will consider that constant pressure to be 1 atmosphere, 1 atmosphere pressure, which is because most processing will be done at a fixed pressure. Now, having determined T L and T S for a given composition, we can repeat the same experiment for a set of alloys for different values of x, x1, x2 and all that. And then if we get this data and we plot it on a diagram like this, here this y axis is the temperature axis, x axis is the composition axis. So, let us say capital N B, this represents atom fraction B. Atom fraction B, it starts with 0, this is 1. We can also do it for weight fraction. Now, atom fraction B, and suppose we have done it for this alloy X. So, alloy X. So, this actually is the T L where, so this is the T L where the solidification begins, this is T S where solidification is completed. So, in fact, what you can think about is what you can do is you pick up a set of alloys. For each alloy you plot T L here, T S here, T L here, T S here, T L here, T S here, and say suppose this is your melting point, this is melting point of A, this is melting point of B, and this is composition or weight percent B or mole fraction B. So, this is 0 B, this is 100% B or 1 atom fraction is 0 here, atom fraction B is 1. And then if you join this, you get a diagram which says that above this temperature state of the material, it is liquid, it exists in entirely in liquid state, and below this T S temperature it exists in solid state. So, here it is solid and here it is liquid. So, the phase diagram gives